So here's what we did Monday, functions of bounded variation, and for reference, I will put the lemma that we spoke about on Monday. So if we have f and g are functions of bounded variation on the interval ab, and we have that c is some real number, then the variation of f is equal to 0 if and only if f is constant. Two, the variation from AB of c times f is the same as magnitude of c times the variation of f. 3, the variation of the sum f plus g is less than or equal to variation of f plus variation of g. 4, for the product, this is less than the sup norm of f, variation of f, variation of g, my apologies, plus the norm of g, variation of g, of f. The variation of absolute value is less than or equal to variation of the function f. And you have this property that is similar to integration, is that variation ab of f is equal to variation from a to c of f plus the variation from c to b of f. Now, if there are any of those results that don't seem trivial to you, I'm happy to prove it. But properties 1 through 3 tells that we almost have a norm. And clearly that the space of bounded variations is a linear space. It's a vector space. All right. So we can make this space into a norm vector space by defining the bounded variation norm of f to be equal to the absolute value of f of a plus the variation of f. So to see that this is a norm, so of course, if f is equal to 0, the norm, well, this is going to be 0. Suppose this is equal to 0. I want to show that f is 0. So the implication is that the variation is 0, and therefore f is a constant. Now, what constant could that be? Well, absolute value of f of a is equal to 0, so that implies that f of a is equal to 0, which implies f of x is 0. That's by property number 1, if you know how to establish it. So notice that if I take the sup norm of a function, it is always less than or equal to absolute value of f of a plus the variation of f. We showed that in a lemma on Monday, right? Remember that? So the implication is that the sup norm is smaller than the bounded variation. In other words, convergence in BV AB implies convergence in the space of bounded functions on AB. So, in other words, convergence in bounded variation implies uniform convergence. So, next is what we want to establish is that the space of bounded variations is complete. Is complete under the bounded variation norm. Proof. Let this be Cauchy in the space of bounded variation. Then we know that we have uniform convergence. And we know that f is in the space of bounded functions. Now we want to show that in fact f is it has finite variation. So what we do is for any partition P, which would be A equal to T0 less than T1 all the way to Tn equal to B of the interval AB. We have variation of the difference Fn minus F over P. It's going to be, let's have it to M. So it's the summation where k starts at 1 all the way to m of absolute value First function is fn minus f. At tk minus fn minus f at tk minus 1. Now if we break it by triangle inequality, this is less than or equal to the summation k equal 1 to m of the absolute value fn tk minus f of tk plus fn tk minus 1 minus f of tk minus 1. Right, all I did is just I have this minus, I just applied triangle inequality and I broke it like this. Now, this is less than or equal to the summation. So we always have n terms, the summation where k starts from 0 to m, and I replace this by the sup norm. So instead of having those tks, I just replace each term by a sup norm, thereby increasing the sum. This is less than or equal, or in fact equals to how many copies we have? We have m plus 1, so it's going to be 2 times m plus 1 times the sup norm. And this goes to 0 as n goes to infinity, because we have uniform convergence. It goes to 0. Now notice that the partition, we actually sum only, for this fixed partition, we only sum m times. So the consequences are that limit as n goes to infinity of v fn minus f p is equal to 0 for any partition p, and that implies that limit as n goes to infinity of the total variation of fn minus f has to be 0 as n goes to infinity. Since it's approaching to 0 over any partition, you can avoid limits, you can restructure it. Actually, in my notes I did it slightly a different way. But you see what you do. When you have this total variation, you replace it. So if you subtract epsilon from it, you can replace it by a particular variation over some particular partition. And then the limit follows. So you can show this more rigorously if you'd like. So the consequence is that if I look at limit as n goes to infinity of fn minus f dv. This is limit as n goes to infinity of fna minus fn minus fa, sorry. Plus the variation of fn minus f. Now this limit is 0. Which implies, of course, that f belongs to the space of bounded variations, because you can just take the bounded variation of f, and that is less than or equal to, or better said, if you take f and you take any partition, that will be variation of f minus fn less than or equal to f minus fn of this partition plus the variation of fn of that over that partition. So therefore, in the limit, that will go to the variation I should say then this is vanishing, so it's going to be less than or equal to some epsilon plus an upper bound, since this is a Cauchy sequence. Where B is the upper bound for all the variations. All right. So it's very similar to integrals, the way it behaves. And there is a function very similar to the one you create using the fundamental theorem of calculus. So what you have is fix f belonging to BV AB and set v of x to be equal to the variation from a to x of f. By the way, this function v of x reminds you of what? Very good. It should remind you of the arc length parameterization. Why is it not necessarily arc length? Is because we are calculating bounded variations of things that are not necessarily curves, and definitely not necessarily differentiable curves or even continuous curves. Okay, so this is like the arc length. And that's defined for x bigger than or equal to a and less than or equal to b. I should make a note that v of a should be 0. Then both v and v minus the function f are increasing. Consequently, we can say that f is equal to v minus f is the difference of increasing functions. By the way, I hope that as you're reading those chapters, you're looking through the homework. Try to solve, not my homework, I mean the assignments in the book. Just try to solve random questions. You're doing that, right? Because I'm looking at it and I feel very greedy. I feel like, my God, this you might kind of skip, and this you might skip. Right? And I would have assigned it all to you, but then I have to grade it. All right, so proof. So given y bigger than x, we can calculate v of y minus v of x, which is just the variation from a to y of f minus the variation from a to x of f. And we can use one of the properties that we have here, namely property 6. So that like with integration, it's like the arc length from a to y minus the length from a to x. And that means the length of the curve from x to y. And that's clearly bigger than or equal to 0. I mean, let's actually add this extra step. Why is it clear that it's bigger than or equal to 0? Well, because the coarsest type of partition is just the partition involving the points x and y. So this is bigger than or equal to just the length of f of y minus f of x, right? So it's like you don't break it apart before that, and this is bigger than or equal to 0, its absolute value. So what it also, by the way, so v is increasing. Notice, however, that we showed more. We showed that v of y minus v of x is bigger than or equal to, if we drop the absolute value, f of y minus f of x. And the consequence is that if I rearrange terms, I have that v of y minus f of y is bigger than or equal to v of x minus f of x, and as the consequence, v minus f is also increasing. All right, so let's just do a quick comprehension check. So we said that if f is in the bounded variation space, f is equal to v minus f, difference of two increasing functions. So the question is this difference of increasing functions unique? So easy question, I hope. Is this difference unique? Right, so basically every function of bounded variation can be decomposed as a difference of two increasing functions. That tells you quite a lot about it's the possible discontinuities, right? Remember, increasing functions only have at most countably many discontinuities. So a function that has bounded variations cannot have uncountably many discontinuities. Also, all discontinuities are jump discontinuities, right? But yeah, so that gives you an easy criterion. Instead of just directly measuring the length, you can just say if it has finite length by noting if it's a difference of increasing functions. Or sometimes notice that it cannot be if it has many discontinuities. But this question is even simpler. Is this difference unique?
It's a function, so it has to be.
Well, the function f, yes, and then we have v minus f.
Well, you mean that decomposition is unique, or the difference between?
Yeah, I mean, so decomposition into two increasing functions. There is one increasing function, and there is another increasing function. Will they always be just for any function f only two, or not?
Oh.
You see what I'm asking, right?
Oh, yeah. So you're asking whether the decomposition is unique?
I'm asking whether the decomposition is unique.
Oh.
So for example, the number 6 is uniquely decomposed into primes 3 and 2, right? So there are no other two primes that will work. So I'm asking for a function of bounded variation, I am able to find theoretically two increasing functions. Will I be able to find another pair of increasing functions? Yes.
You can just add one to each.
Exactly. As I say, very trivial question. I'm just asking this to see that you have a pulse. All right. Of course not. So we can take u equal to v plus c, and well, and r equal to, or w equal to v minus f plus c. Okay, the composition is not unique. Of course, you can ask a more difficult question. What if I don't allow constants, right? If I just, it has to be not just has to be of a different type. Like with integration, right? It's very similar to integration, right? If you found one antiderivative, the antiderivative plus a constant is just another thing. You see, this looks like an antiderivative. So it's like an antiderivative plus a constant, right? Are there other types of antiderivatives? Maybe. That's maybe a more interesting question, right? Maybe on your exam. All right. So where are we? So, all right. So corollary. That's Jordan's theorem. A function We actually already stated it's called a function is of bounded variation. If and only if it can be written as a difference of two increasing functions. Looks almost the same as this theorem, except for one tiny detail, which you might have noticed already. So proof. If f belongs to the space of bounded variations, the result is already established. Conversely, if I can write f as alpha minus beta, where alpha, beta are increasing functions, then the total variation of alpha is simply alpha of b minus alpha of a. And the total variation of beta is simply beta of b minus beta of a, which implies that both alpha and beta belong to the space of bounded variation. Which implies that alpha minus beta is in the space of bounded variation by what? By number 3. Okay, so make sure that you can prove those all those statements. They're pretty simple.
Could you please just say one more time why the total variation of the alpha equals to alpha beta?
Yes, the function is increasing, so you can just here take variation of alpha under the partition P. So just pick any partition, right? But if the partition is very fine, it will be a close approximation to the full variation, right? So then what is that? Then what we have is summation k equal 1 to n of absolute value alpha tk minus alpha tk minus 1. Okay? Now the absolute value here is not necessary because the function is increasing, right? The partition, I should say, here, partition here is a equal to t0 smaller than t1 all the way to tn equal to b. Okay, that's the partition. So tk is bigger than tk minus 1, and therefore, by the fact that the function is increasing, I can drop the absolute value. Okay? And this is a telescoping sum. What survives is only alpha t to the n minus alpha t0, which is alpha of b minus alpha of a. And since this is true for all partitions, that will be true for the bounded variation. Right?
Thank you.
Sure. So another corollary each f. So this topic for now is easy, right? I hope, right? Yeah? I just heard a sigh. I hope that's like ice. It's okay, right? It's just like it's just like Riemann sums, pretty much. So each function in the bound variation has, in the space of bounded variation, has at most countably many points of jump discontinuity. Okay, that's clear because it's the difference of two increasing functions. Increasing functions are mostly continuous.
Wait, the difference between two increasing functions is not necessarily increasing.
No, I didn't say that, but the discontinuities are not too bad, right? If you take the discontinuities are at most the combined discontinuities of both increasing functions, which is countable.
So it's still monotone, right?
The difference?
Yeah.
No, not necessarily. You can right away see that by just thinking of functions of bounded variations that go like this, right? No, difference can be quite a few things. It's actually a little bit. I think it's a little bit surprising that you can write everything as a difference of two increasing functions. I haven't been thinking about it in a while, so yeah. But just out of the blue, just right now, I think it's a little surprising, right? Now you might ask, why would you want bounded variation? Where if you're going to read Conway in complex analysis, right? One of the few books that really torture you about line integrals, right? So line integrals, you integrate along a curve, and then you have to be very precise about arc length and whatnot, and then you start bothering about the cases where arc length is not necessarily defined. So, yeah, and then if you consider Julia sets, which are in complex dynamics, which can be sometimes very, very complicated curves, stuff like that, you start trying to create some hopeless type of descriptions for them. But in essence, it's just like a generalized arc length. That's what we're doing, right? It's just pretty much just take a curve, measure its length.
Sorry, Professor.
Yeah.
So what is exactly the difference between the arc length and the total variation?
Exactly. What's the difference? Now, can anybody tell me what's the difference between arc length and total variation?
Total variation only does vertical distances. Arc length does horizontal as well.
Well, I mean, we basically we've broken this problem to just measure, I don't know, horizontal or vertical, true, right? So, but this might be, but let's say total variation measures the distance of a particle traveling, in our case, traveling on a straight line, right? But there is a bigger difference. So I would say
Arc length can only measure continuous distances.
yeah, in continuous. In fact, with arc length, right? What do you do? With arc length, you assume that you have a curve that is that it's possible to approximate this curve with line segments, right? So any curve in the arc length that you're doing, you're just building it up as a bunch of segments that are line segments. In other words, in arc length, you usually have a function that is very differentiable, either always differentiable or piecewise differentiable, right? Piecewise smooth, right? We're going to see examples where bounded variation becomes arc length in the normal cases, right? But then you can have curves that are very, very irregular, so irregular that they cannot be approximated by straight lines. So, for example, if you take the continuous nowhere differentiable function, right? Remember that one, right? With the teeth. Right, so this function, I mean, you cannot quite measure arc length because you cannot take derivatives anywhere, but you can ask about whether or not it's of bounded variation, for example, right? Which or you can ask over an interval, is it going to be of bounded variation?
So is it safe to say, like, for most local cases, the total variation is the same as?
For many cases, for us, yeah, for many normal cases, like reasonable, like you just think it's just arc length, right? But this is something that is possibly stronger than arc length. It's able to deal with cases that arc length is not able to deal with, right? So definitely, we have discontinuous functions here that we can consider. All right. Theorem. So maybe the last thing we prove today, fix f in the space of bounded variation. And let v of x be equal to this function. Then f is right or left continuous at x if and only if v is right, left, continuous. Proof. So if x is smaller than y, we have that v of y minus v of x is always bigger than or equal to the absolute value f of y minus f of x. Right? Hence, if I look at right continuity, if I'm assuming that this function is right continuous, so we have v of x plus. That means the limit as y goes to x from the right. Right? So, in other words, if I assume that v is right or left continuous, that will force f to be right or left continuous. So for example, if I consider this at y, so v of y minus v y minus will be bigger than or equal to f of y minus f of y minus. Thus, if v is right, left, continuous, at x, then so is f. Now suppose f is right continuous at x. And here we have x smaller than b. Given epsilon bigger than 0, there exists delta bigger than 0, such that f of x minus f of t is less than epsilon over 2 whenever x less than or equal to t less than x plus delta. So for this epsilon, choose partition P of x to b such that this partition is a good approximation to the total variation. That means so by increasing p if necessary, we may assume so if this partition is something like x equal to t0 less than t1 less than tn, which is b, we may assume that this satisfies in other words, we partition it so that there is going to be one element of the partition very close to x. And then we have and if we break this partition, we have f of x minus f of t1 plus the variation of f over the remaining elements of the partition and that's less than or equal to epsilon over 2. Since this is already approximated, we have right continuity. T1 is close enough to x, so this is less than epsilon over 2. And this variation is less than the variation from T1 to b. And the implication is, of course, that you see you have minus epsilon over 2, epsilon over 2. You can bring those things on one side. So we have epsilon is bigger than or equal to the variation from x to b of f minus the variation from t1 to b of f. And this is simply the variation from x to t1 of f, which is v of t1 minus v of x, which is bigger than or equal to 0. So it's squeezed by epsilon. So that means that v is right continuous. And similar argument will hold for left continuous. Okay? You might ask yourself, for example, this thing, is it differentiable? Is the function v differentiable? Yes or no? You can think about it. Right? It's very similar to the fundamental theorem of calculus. Right? So see what you can say. Or what is the condition for it to be differentiable?